Welcome to this session on exploiting data parallelism for R scalability. In this session, we look at achieving data parallelism in R and how Oracle Machine Learning for R makes it easy to do this with database data, while simplifying deployment in applications. My name is Mark Hornick with Oracle Machine Learning Product Management. To set the stage for talking about parallelism, the goal is to improve performance by running multiple computations concurrently. Like most things, achieving parallelism can range from simple to complex. Typically on the complex side is individual algorithm parallelism. Many algorithms are implemented with serial processing in mind, and to gain the benefits of parallelism, some require significant redesign, and others, by their very nature, simply can't be parallelized. Now, toward the other end of the spectrum is data parallelism, where the basic algorithm is run on data in parallel using multiple threads or processes on data partitions. So let's relate that to R packages. Some operate sequentially, so there's no parallelism enabled by the package. Some may use, for example, matrix algebra functions and can leverage implicit parallelism via optimized math libraries, like Intel's MKL. So there's no algorithm redesign needed. Still, other packages are designed with parallelism in mind, but may rely on specific parallel packages and infrastructure. Now, while achieving algorithm parallelism may require a package redesign, data parallelism techniques can be applied to any of these. So for a moment though, let's talk about scalability and performance. One of the first considerations for scalability is data movement. Moving data, especially large volume data, can be problematic. There's the time it takes to move it into memory or local disk, whether from a flat file or a database. And this can be costly as bits travel across the wire, especially if cloud vendors charge for data movement. And we also need to consider data backup, recovery, and security. Ideally, we could leave data where it lives and perform processing locally. Let's discuss another scalability concern, available memory. Most R packages expect data to fit in memory. For example, when filtering or transforming data, or building or using machine learning models. Of course, if the data doesn't fit in memory with enough left over for processing, we need a different approach. With data parallelism, we achieve scalability by partitioning data and processing each chunk. If the data resides in a single file or table, we first need to partition that data, which allows us to process it sequentially. So we've addressed scalability, but what about performance? To achieve performance, we introduce parallelism. And if we spawn multiple R engines, we can expect to see elapsed time reduced significantly, perhaps by as much as a factor of the number of R engines used. This type of approach is often referred to as embarrassingly parallel, since it's so easy to implement. So what are some use cases that can benefit from data parallelism? Well, perhaps the most obvious one is scoring data at scale, which is inherently an embarrassingly parallel problem. Other partition data computations include computing statistics or generating plots like per customer or per region. Model building too can benefit by using different data subsets to create ensembles. And Monte Carlo simulations may be run on data that is randomly generated or selected. So let's take a specific example of how we might use data parallelism to make predictions using R's parallel or for each packages. To start, we'll build a naive Bayes model to predict species. We're using the familiar iris dataset. And after connecting to the database and pulling the data into memory, we define our function to build the model and save it to disk. Let's start by using MCLapply from the parallel package for scoring data. While we're using the iris dataset with only 150 rows and 5 columns, which easily fit in memory, consider the scalability implications at each stage if we have 100 million rows to score. Now connect to the database and pull the data into memory. And to enable data parallelism, partition it in some number of groups. Here we chose 15 with 10 rows in each. On larger datasets, imagine each partition consisting of many thousands of rows, but this depends in part on the cost of producing each scores and the available memory. Then we load our model from disk and invoke MCLApply with our partition data and scoring function. To get maximum parallelism, let's choose 15 cores to match the number of partitions. Now, since the result comes back as a list, we first R-bind the results before writing those scores to a database table, although we could iterate over the list of data frames to insert them in the table incrementally. Now, finally, we compute a confusion matrix off the actual and predicted values. Of course, all of this data needs to be present in the local R environment for this to work. We can do something similar using the for each package, but here we first explicitly make and then register the cluster, and when finished, stop the cluster to free up resources. So what scalability concerns do we have with this approach? Well, we need to pull the data from the database to the client and then partition it. The partition data could actually consume significantly more memory than the original data, so we need to factor this into any solution. Since our model is stored in a flat file, we need to ensure our production process has access. We also need to factor in backup, recovery, and security for our data, model, and scripts. All the processing occurs on the client machine, so it needs to be sized to meet the need. And lastly, the result is returned as a list of data frames that need to be R-bound together. And if this itself is a large result, additional memory considerations may come into play. We address these concerns with Oracle Machine Learning for R leveraging the database as a high-performance compute engine. OML for R avoids pulling data to the client R engine and consuming client memory. The database automatically spawns and manages R engines with the benefit of system-supported data parallelism. And we can store R objects and user-defined functions in the database, getting the benefit of database-level security, backup, and recovery, along with access control. As we'll see, database tables are accessed through data frame proxy objects with overloaded functions that produce SQL transparently behind the scenes. And this includes overloaded dplyr functions for manipulating data in the database. Part of the OML for R capabilities are in-database machine learning algorithms that are exposed through an R API using the R formula. And these algorithms are designed for parallelism and scalability. All processing for model building and scoring occurs directly in the database using these algorithms. Here's the code that builds the model, storing it in the database, while having the database spawn and manage the R engine to process it. Our UDF builds a model to predict species using a data frame passed as the first argument, and saves the model to the database in what we call a data store, using ore.save. The return value is simply the Boolean true. Next, connect to the database. Create our UDF in the script repository and get a proxy object to the iris table. Then we invoke Rqroweval, providing the proxy object iris, the name of the function in the script repository, the name of the data store under which we'd like to store this model, and to automatically connect to the database from the spawned R engine to access the data store. The database environment spawns an R engine, loads the UDF and iris data from the database, and when finished, we have our model saved in the database and the R engine is released. We can invoke our model building UDF from SQL as well, say to allow our application to build this model. Using a select statement with the Rqtableeval function, we specify the source data using a SQL query. In this case, select star from iris. As in the previous example, we specify the function arguments. Indicate that the result should be returned as an XML string. Recall the result is just returning true, and give the name of our UDF just created in the script repository. With the model created and stored in the database, let's define a function that uses that model to make predictions. As before, ORE script create stores the UDF in the database script repository. We can also store our UDF using PL/SQL with the function rqscriptcreate. And this allows DBAs or SQL users to receive UDFs from R developers to deploy them themselves, perhaps in secure production environments. So now, let's use OML for R to get data parallel behavior using our scoring UDF. After getting a proxy object to the iris table, we provide it to Rqroweval along with the function in the script repository. And that we want 10 rows to be processed at a time, do this in parallel using 15 R engines. The fun.value parameter specifies the resulting data frame structure so it can automatically create a single result, as opposed to a list of partial results. Invoking Rqroweval causes the database to spawn the R engine, load the UDF and data partition into each, and collect the results, which are presented as a single ORE frame proxy object. And this is important since results themselves can be large, and we don't want to pull results to the client unnecessarily. Next, we create the table batch scores and use the overloaded table function to compute the confusion matrix in the database on the batch scores proxy object. Note that only the confusion matrix itself is returned to the client without the need to load large volume data to the client R engine. Here's the corresponding SQL invocation using Rqroweval. You'll see some familiar parameters from the previous example. We have the data iris with a parallel hint to indicate that we want 15 R engines. We have the parameter list, the result structure, the number of rows to feed in each invocation, and the name of the UDF in the script repository. So let's see a brief demonstration of OML for R embedded execution. So we're looking at RStudio, and we're going to run our script to explore exploiting data parallelism using Oracle Machine Learning for R. So the first thing that we'll do is to load the ORE packages, and then we'll connect to the database. And what this does is to create a set of proxy objects that we can now use that correspond to database tables. We'll look that we have the iris proxy object. We see that it's of type ORE frame, and we can see the first few rows of that data that have been retrieved from the database. Next, we'll define our build NB model function. We'll create that script in the script repository, giving it the same name as the function. So from here, we invoke ORE table apply. So what's just happened? We have spawned the R engine, loaded the function in data, built the model, and stored it in the data store. And so we have our data store, naive Bayes model iris species. We can see its size and creation date. And if we look at the contents of that, we see that we have an object that is named mod, and the class is naive Bayes. So now let's score using this model. So our scoring function is going to again load the library, load the data store that contains our model. We're going to use that model to make predictions and then return the actual and predicted value. So we'll create that script in the script repository, and now we'll use Rqroweval to invoke that. We're going to pass again our iris data set. Our function name is scoreNBModel. We have the data store name where we're going to be loading that model from, that we need to connect back to the database to access the data store, and that we want 10 rows, 15 R engines, and this is what the result is going to look like. So let's run that. And we see the result of our predicted class is an ORE frame as well. Let's now create the table batch scores. So we're going to first drop that table and create that table. And it's at this point where we're actually trying to access the results that this is being processed and the table is created. Now let's look at the first few rows in our batch score proxy object, and we see some of the results. But we can use that same ORE frame to use the overloaded table function to give us our confusion matrix. Well, let's take a look at SQL Developer now to show how we can do the same thing from SQL. In this case, we're going to use Rqtableeval. We have our cursor where we're selecting star from the iris table, passing in our arguments. We have an XML string, our build NB model as the function that we're going to invoke. So let's just run this. And this is showing that we got back true. Okay, well, we've just built our model from SQL using the Rqtableeval function, passing in the iris data. But as we mentioned, you can store your scripts in the script repository from SQL as well. And here we're going to store again the score NB model function in the database using the SQL API. So we've now stored that in the script repository. We can see that this script exists in the script repository also from SQL. Let's drop the table batch scores and create it dynamically using Rqroweval. And we're going to do a ctask, the create table as select, using this query that we showed in the slides. And from here, we can use that table that we've just created to get our confusion matrix directly as a SQL query. So that ends our script with the SQL developer. So far, we've seen the table eval and row eval functions in our examples, but there are others to support additional use cases. For more information, here are a few resources, including blogs, additional code examples, and documentation. So thanks for joining this session, and I'm happy to take any questions.